Segment 5. So we left you with a little bit of a cliffhanger on an H2SO4. We're looking at these two different structures and we're asking ourselves which one is correct. Is it this one or is it this one? And we kind of led to the idea of experimental stuff. So here, how do we know which one is accurate? Well, again, we're going to rely on experimental evidence. In this case, bond lengths from X-ray data. So what we can do is we can make a crystal out of different things. We can do single crystal X-ray diffraction, and based upon how X-rays are reflected out and how they're deflected, if you will, it gives us an idea of what the angles and positions are of the different atoms, and that would lead to distances between the atoms. And so the SO bonds here that have no hydrogen attached appear to be shorter. They're 142 picometers, whereas the ones with the hydrogens seem to be longer at 157. So that's going to indicate that there are two bonds that are shorter and the other two are going to be a little bit longer. The structure with the S double bond O then for the two oxygens without hydrogens would come off to be more accurate. And so that's going to be what we consider to be the preferred Lewis structure. And again, that's okay for sulfur because sulfur has that d orbital. So even though it's violating that octet rule, it works. Okay. Another way we can see that it's going to work out is what we call formal charge. Now, for the formal charge, what we're going to do is look at what the apparent charge is on a single atom. You can think of it more like a bookkeeping method. Okay, so this is not going to represent real charges, but it gives us an idea of whether or not the atom is participating with its electrons the way we would expect it to. So the formal charge then equals the number of valence electrons minus the number of unshared electrons plus 1/2 of the bonding electrons. Okay, so again, the formal charge would be equal to the valence electrons then minus the bonding atoms plus half of the unshared electrons. Indicate the formal charges by placing them in circles around atoms. Now it sounds complex, but we're going to jump right in and you'll see what I mean. So here's that the SO4, H2SO4. And if we look at the formal charges, we're going to take the number of valence electrons, right? So we know that oxygen here should have 6 valence electrons. We're using up 2, 4, 6, so the number of bonds, so we're going to subtract the number of bonds to the atom, which was 1 bond. Okay, so minus 1, so I should say minus 1, plus the number of unshared, which was 6. So we have 6 valence electrons minus 1 from the bond plus 6 unshared electrons. That gives us -1. So that's where the -1 here is coming from. Okay, so for structure 1 then, for the FC of the S, we have 6, because it's also in group 6A, minus 4 bonds plus 0 unshared electrons. So that's going to give us a +2. For the hydrogen, it works out to be 0. For the oxygen, we saw that it was -1. Okay. Now, if we were to make double bonds, and we look at the formal charge for the oxygen with a double bond, we now get 6 minus 2 bonds plus the 4 electrons, and that's going to give us 0s. Now for structure 2, if we recalculate the sulfur, we can see now we have the sulfur with the double bond. So now we have 6 bonds plus 0 electrons. That gives us a formal charge of 0. And all the while, of course, the oxygen then is also going to be 0. The hydrogen remained at 0. The single bonded oxygens also become 0. Okay? So structure 2 then, even if you didn't know that X-ray data, by looking at the formal charges, we get all 0s. So we can also use that to determine that it's going to be the better structure. Okay? So no formal charges on any atom in structure 2. So the conclusion for that then becomes when several Lewis structures are possible, those with the smallest formal charges tend to be the most stable and thus preferred. Okay? Now most stable Lewis structures, The lowest possible formal charges will always be best, and all of your formal charges should be less than or equal to 1, whether it be positive 1 or negative 1. Any negative formal charge has to be on the most electronegative element. Okay, so if there is a formal charge and it's negative, it has to be on the electronegative element. Now, hopefully that makes sense. We know the electrons are going to spend more time there, and so we're going to give it the formal charge of the negative. Now for CO2, if we draw out CO2, we throw in the electrons as such. We can do the math here, and it's going to end up with 0 electrons. Now before, what we would do is start to put pairs of electrons in between the carbon and the oxygen to make sure that the carbon also gets its octet. So as drawn, we can see it only has 4 electrons, which means we're going to need 2 extra bonds to oxygen to complete that octet. So now there's several different ways we can do this. We can take 1 oxygen and push 2 pair in, forming a triple bond and a single bond. Now everybody's happy. Each one of them can donate 1 pair, that gives us 2 double bonds, or the other one can donate 2 pair, and that gives us another triple bond. Now remember, I kind of let the cat out of the bag with this, because if you think about in the last segment, I said nature always prefers symmetry. So if nature always prefers symmetry, then that kind of gives you an idea that, this one's going to be best. But there's got to be a better way. We can't just say, oh, well, nature prefers symmetry and that's the answer. There's got to be some way we can figure out how we can do that. And of course, what we just saw was formal charges. So which structure is the best? I don't know. Let's take a look at the formal charge. So the formal charge for carbon in all 3 of these is going to be 0, right? It's got 4 bonds, 4 valence electrons. So 4 minus the 4, and none of these 3 cases doesn't have a lone pair. So that's going to be a plus of 0. And of course, 4 minus 4 plus 0 would be equal to 0. For the FCO single bond, right? So here we have 6 valence electrons for oxygen, 1 bond plus 6 lone pairs gives us a negative 1. Now the negative 1 would fall on the oxygen, which means that's going to be okay. If we have a double bond, we have 6 minus 2 for the double bond, plus only 4 valence electrons now gives us 0. And now the formal charge for the oxygen with a triple bond, we've got 3 bonds, only 1 lone pair, which gives us a plus 1 on the oxygen. All right, so we have plus 1, minus 1, and of course zeros on the CO2 with the 2 double bonds, and then minus 1 plus 1 on the third structure. So if these are our 3 structures and these are the formal charges, then once again the 2 double bonds will end up being the right answer. All right, so the central structure will be our best structure. Here all of our formal charges are going to be equal to 0. All right. Now we can take formal charges one step further and use that to explain boron chemistry. So boron we saw could be deficient. So let's take a look with formal charge. So BCl3, why doesn't a double bond form here? Now we said earlier it was because the chlorine is a terminal atom. It only has 1 electron that it wants to receive. It got that from the boron and doesn't want to do anything else. That's partially true, but let's take a look at it from the perspective of the boron. The formal charge for boron in this case would equal 3 minus 0 minus 3. So it has no lone pairs, and it's using 3 electrons in the single bonds. The formal charge on the chlorine in all 3 of these situations would be 7 minus the 6 lone pair, well, 6 electrons from the 3 lone pairs that it has, minus the 1 that's in the bond. That also gives me 0. So just drawn as BCl3, all the formal charges would be 0. So the molecule has the best possible structure just the way it is, even though it's electron deficient for the boron. That means that we don't need to form the double bond. So we're going to go ahead and violate the octet rule for the boron in that situation. All right, so we've looked at a lot of these electron structures. We've then looked at a few exceptions. We've looked at formal charge, and let's see, let's try to start putting it all together and do some problems. What is the formal charge on xenon for the following? Okay, so again, what's the formal charge? We know that it's a noble gas. It should be 8 valence electrons. In the first structure, it has 4 bonds. In the second structure, it has 6 bonds. So hopefully you've selected D, +4 and +2. What is the formal charge on each atom in the structure below? So what is the formal charge of each atom on the structure below? All right, so oxygen has 6, 1 bond, and 6 valence electrons. Nitrogen starts with 5, has 3 bonds, and 1 lone pair. Sulfur has 6 electrons, 2 bonds, 4 electrons in the 2 lone pair. So our answer should be E. All right, the next concept we're going to look at to help us with our structures is going to be resonance, explaining multiple equivalent Lewis structures. So you can imagine I could give you a couple of formulas where even with formal charges, it would all balance out. And so now you'd have several different structures that don't have any discrepancies in their formal charges and meet all the octet rule. So then what do? Well, we're going to use formal charge to decide between 2 different Lewis structures. We need an explanation of equivalent structures from that point. So the concept is then resonance. Resonance provides the way to interpret equivalent structures. So when a single Lewis structure fails, so here we go, we have NO3 with a minus charge. Nitrogen gives us 5 electrons. Oxygen, there's 3 of them, we have 6 electrons. Now because it's a charged species, -1, we're going to add that 1 electron in. So we actually have a total of 24 electrons. We'll draw single bonds to all of our atoms. And of course, we put a formal charge on the outside. All right, so we don't know exactly where that -1 is in this structure. We're going to say it's somewhere in that structure, it's a -1. That means I'm going to subtract 6 electrons for those single bonds. That leaves me with 18 electrons. Next, I'm going to put 18 electrons in, right? Because I'm going to put all the lone pairs around the oxygens to fill their octets. And that leaves me with 0 electrons. Now when I calculate out formal charges, I can see that the nitrogen has 5 minus 1, that's 4, minus 2, excuse me, minus 3, that leaves me with a +1. Excuse me, a +2, right? Because that's, oh my gosh, I'm losing my mind. Sorry about that. Let's try that again. We have 5 electrons for the nitrogen. We have 3 bonds and no lone pairs. So that's going to be a +2. For the oxygens, we end up with 6 minus 1 minus 6, which gives me a -1. So it means each oxygen then would have a -1. If I do it this way, we get -1, -2, -3, +2 would be -1, which is what we have overall, so that should be fine. Now another way to draw this would be to take one of these pair and stick it in here. Nitrogen really doesn't want to be +2. Nitrogen doesn't want to be plus at all, but it definitely doesn't want to be +2. If I move just one of those pair, now I have nitrogen as a +1, one oxygen at 0, and the other 2 will be a -1. We still have an overall charge of -1 though. So that's another possible structure. Now Lewis structure predicts that one bond would be shorter than the other 2. That makes sense, right? So if one of them is a double bond and the other 2 are single bonds, then the double bond should be shorter than the single bonds. However, experimental observation shows that all 3 NO bond lengths are the same. They're all shorter than single bonds, and they're all longer than a double bond. That means we're going to have to modify our Lewis structure, and the electrons cannot be distinguished between the oxygen atoms. So we can write two or more possible structures simply by moving where electrons are. Okay, so in other words, we're going to move the electrons around that central atom. So we drew a double bond to an oxygen. Well, how do we know it was this oxygen? So we'll call that oxygen 1. Maybe it was oxygen 2. So there's our next structure, where oxygen 2 now has the double bond. Well, why does it have to be 2? Why can't it be 3? And there it is. The third one now has a double bond. Now, this is what we're doing to account for the idea that all the bonds are the same length. So we're going to have multiple Lewis structures for a single molecule. No single Lewis structure is going to be correct. Notice the arrows between the structures. We've drawn out 3 different structures, and we have double-headed arrows, saying that this basically goes in a circle. Okay? The structure is not accurately represented by any one of these Lewis structures, and the actual structure would actually be the average of all of the possible structures. Now we can draw one resonance structure that's going to make it look that way, but it looks kind of funny. And what we do is we take dashes and put dashes in there and say it's not a full double bond and it's not a full single bond. So there's more electron density here than just a single bond, but there's less than there is for a double bond. We call this a resonance structure. So Lewis structures assume electrons are localized between 2 atoms. In resonance structures, the electrons are said to be delocalized. Okay, that means, in other words, they're smeared out over all the atoms. So we can move around the entire molecule to give equivalent bond distances. And so the resonance hybrid drawing would have those dashes in it. Okay, and that's just a way to depict that resonance delocalization. All right, let's take a look at another example. So CO3 2-. And I see we have a typo on the slide. So this should be carbon at 4 electrons. Doesn't give us 5, it gives us 4. And then we have a -2 charge, so that's going to give us 2. Luckily, we still end up with the same electron count, 24 electrons. All right, so we're going to jump right to C with a double bond and 2 single bonds and a 2- charge, right? And so in the math, we're not doing that though. We have 2, 4, 6. We're going to take away 8. And so this is not 18 now, but 16 electrons. I think that's because we added when we shouldn't have. Jump in structures here. I guess if we try it again, right? So we should have started with this one, not this one. I guess they got their structures flipped around here. Anyway, so we would have had 16, 2, 4, 6, 8, 10, 12, 14, 16, 18. So if we make this a single bond, try to make sense out of what they've written here. So here only carbon has 6 electrons, so the double bond is then needed. So instead of jumping to that first one, we should have ended up with this one as our last one. And so here we have the 16 electrons. So hopefully that didn't confuse you too bad. They're typos. 2, 4, 6, 2, 4, 6, that's 12, 13, 14, 15, 16. Here we have a formal charge of 0, a formal charge of 0, formal charge -1, formal charge -1. And again, we can rotate that double bond around, much like we did with the last structure with the NO3. And so all have the same net formal charges on carbons and oxygens, which is the carbons are all zeros. 2 of the oxygens will be -1, 1 oxygen will also be a 0. Okay. And again, resonance structures then are not always going to be equivalent. 2 or more Lewis structures for the same compound may or may not represent electron distributions of equal energy. So how do we determine which are good contributors then? Well, number one, we want to make sure we're satisfying all the octets. Now we've talked about some of the electrons or some of the elements where that won't happen. But if we're looking at, say, carbon, where we don't have a d orbital, right? We're in the second period. We don't have a d orbital, therefore we should satisfy the octet. Any of the other elements in period 2 are going to be that same way, right? With the exception we had boron and beryllium. There's exceptions to everything in chemistry, I get it. All atoms have as many bonds as possible. Okay, so if they can only have one bond, then they only have one bond. If it requires a double bond, then that's fine. If it's a triple bond, make sure they're atoms that can have a triple bond. Okay, none of them should ever have a quadruple bond. That doesn't happen yet, not until we get to metals. Formal charge, in theory, most cases, is going to be less than or equal to plus minus 1. Okay? Any negative charges are always on the most electronegative atoms. All the negative charges on the most electronegative atoms. So we saw a nitrogen-oxygen situation, and we had a -1 charge, and if you flip back, you'll notice that the oxygen got the -1, not the nitrogen. And that's because oxygen is more electronegative than nitrogen. All right, so drawing good resonance structures then, all must be valid Lewis structures. So you can't have electrons just anywhere doing anything. Make sure only the electrons are shifting. So usually double or triple bonds or lone pairs are going to be needed. The nuclei themselves cannot move. The bond angles must remain the same. The number of unpaired electrons, if any, must also remain the same. Major contributors are the ones with the lowest potential energy. And the resonance stabilization is most important when delocalizing the charge onto 2 or more atoms. All right, let's take a look at another example. NCO. We'll finish this up and then we'll finish this up and then we'll do a couple of your turns and we'll call it quits. So for NCO, we have carbon with 4 electrons, nitrogen with 5, and oxygen with 6. We have a formal charge, a total charge of -1. That gives us 16 electrons. Here, carbon will be the central atom, and so we're going to have nitrogen connected to carbon, connected to oxygen, and the whole thing has to be a -1. So we're going to have 4 electrons tied up in our single bonds, leaving us 12 electrons in excess. We'll fill in the electrons for the 2 terminal atoms. That leaves us with 0 electrons. So at this point then, we can start to imagine that we're going to have several different possible structures. In our first structure, we're going to take 2 pairs of electrons, stick them both in. That gives us a triple bond to carbon, leaving a single bond to the oxygen. We can have both the nitrogen and the oxygen each donating a pair. And then last, we'll have the oxygen donating the 2 pairs. Now, what are going to be our possible structures? Well, if we look at formal charges, for this first case, we get carbon 0, nitrogen 0, carbon 0, oxygen -1. In our second one, we have nitrogen with the -1, carbon with 0, oxygen with 0. In our last one, we have nitrogen with a -2, carbon with 0, oxygen with a +1. Now for this last one, we know this is not acceptable, right? We can't have that +1 on the most electronegative atom. That doesn't make any sense. So this one is no good. This one we say it's okay. So here we have the -1 charge on the nitrogen. We would expect the electrons to spend more time with the oxygen, which is why this one becomes the best. All right, so resonance stabilization then, actual structure is more stable than either single resonance structure. We see this big time when we look at aromatic compounds in organic chemistry. So here we have a 6-membered carbon ring. So this is a benzene ring. So each angle here, each point in space would be a carbon, like so. And then there is also an understood unwritten hydrogen coming off. So if you're wondering where all of carbon's electrons are, that's where they are. There's actually hydrogens on each one of those carbons. Now here what we're doing is rotating the double bonds around the ring. That's going to give us 2 resonance structures. Rather than having 2 resonance structures, what we'll do is we'll put a circle in the middle, saying that all these electrons are sort of resonating around this ring. Okay? So for benzene, the extra stability works out to be about 146 kilojoules per mole. And we refer to that as the resonance energy. So this is extra stabilization energy from that resonance. Okay? Don't worry about where that number is coming from. Just understand that because of the resonance structures, we actually have extra energy in that molecule. Your turn. Which of the following is false? Not all resonance structures for a given molecule are going to be equivalent. Well, it's going against exactly, let's see, which of the following is false? Not all resonance structures are for a given molecule are equivalent. No, they all have to be, right? Resonance structures indicate that the molecule rapidly switches between multiple electron distributions. Resonance structures are necessary when a single Lewis structure is not sufficient to depict the electron distribution in a single molecule. And formal charges are calculated the same way in resonance structures as in other structures. Okay, so D is true. Resonance structures are necessary when a single Lewis structure is not. That's true. Resonance structures indicate that the molecule rapidly switches between multiple electron distributions. And not all resonance structures for a given molecule are equivalent. They say the answer is B. I'm not liking their answer. I think it's A. All right, which of the structures below exhibit resonance? Hint, there is more than one. So which of the following structures below exhibit resonance? Hint, there is more than one. Well then, how are we going to be able to pick the right one? All right, so let's start with water. Does water have any resonance structures? No, none for water. So we know it can't be B. C3H2, CH2CH. So what's going on there? So here we have a CH3 connected to a CH connected to a CH. Well, something's not right here because you have CH3, CH2, CH. Just have a carbon there with no double bond. It doesn't make any sense. I'm not even sure what that is. That can't be it because I don't even know what that is. Doesn't make any sense. All right, so now we get some nitrogen-oxygen compounds to deal with. So let's see, we have NO2. So let's see, we have 5 plus 12. That's 17 electrons. We just used up 4, so we have 13 left. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's going to leave us with 1. We'll put that 1 on the nitrogen. We'll now have to take a pair and stick that in. So which oxygen is going to put in that pair? We're not sure. So this one has resonance. N3 minus. So that means we have 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so that's all of our electrons. So of course, to make that nitrogen in the middle happy, we could do that. Or we could do just one of these at a time. So this one has some resonance structures. N2O, where nitrogen is the central. Whoops, N2O. So this would be another nitrogen there. I think that one does as well. So we have 3 of them. And so there's A, C, and D, all potentially have resonance structures. All right, went a little long on this one, 30-minute segment. Sorry about that part. But that will finish that up. We have one last topic to hit, and that's going to be coordinate covalent compounds. So they'll be a little bit different, but we'll see how that's going to work out. So hang on for that last segment.